Okay, so basically what we see here on the first screen is if we go through the steps to define the rig we're working with, once we've gone as far as setting up our drill string, we can start to simulate rig functions and calculating volumes. And then after we've done that, once we set up and defined our mud layers and imported the survey data, then we can start calculating bottom hole pressure. We can simulate drilling in conventional mode up to the point of fracture, and then transition over into PMCD, drilling ahead in PMCD, and then we can simulate coming out of the hole, balancing the well again to open to surface and remove the BHA. So let's get started. Here we go. Let's first off say, and I should say most of my drilling experience is taking place in Kazakhstan, so this simulation is going to simulate drilling conditions, rough drilling conditions as they were in Kazakhstan. So let's say we have decided we are going to set our 9 5/8 casing string, and we're going to set that casing string at, let's just say 10,500 feet. Okay? So we're from surface to 10,500 feet with 9 5/8 casing. We're going to say we're going to drill ahead in an 8.5 inch hole. We're going to call the bit, we'll fill a standard 1 foot. Then we're going to, because we don't need an MWD at this point or anything, we've drilled to the point right above the carbonate, we're going to just go ahead and drill with a motor in the hole. We're going to call that, say, 29 feet long, 6.5 inch motor. And on top of that motor, for some BHA weight, we'll throw in some collars, a couple hundred feet of collars. And then you can see we're starting to populate already. And then on top of those collars, we'll just throw on some 5-inch OD, 4-inch ID drill pipe. And we'll say we're going to drill down to, let's say 11,950 feet, something like that. Okay, so plus the collars, plus the motor, plus the bit. Okay, so now we've entered in our drill string, our BHA, our bit, and we have our casing, 9 5/8 casing set to 10.5. We got a 5-inch drill pipe with some 6 5/8 collars. Just a BHA's got a motor on it and a bit, and we're ready to go. So now, if we want to put in our mud, define our mud, we can say that we're going to drill with a 15 pound per gallon mud. And if we want to put in our survey data, we can pull our survey data in from this CSV file. Now, our software is a directional software also. It runs on minimum curvature. So we can calculate surveys from surface. So we're going to load that in. Our survey data is loaded. Now, we're just going to simulate the drilling, and I'm going to slide this bit onto bottom. We're going to say that bottom is 12,180 feet, and based on our calculated survey point, our TBD is 11,291.46 feet. We have our casing volume, our drill string volume, total angular volume, total volume. And our average mud weight here is 15 pounds per gallon with a calculated bottom hole pressure of 8,807.34 PSI. The bit is now at 12,180 feet. And we're going to say we have a fracture right here. So the first step we do is we pull this bit back up into the shoe. Okay, so we're going to pull the bit somewhere about there. That feels about right. And at this point, if you want to pause the video and double check all our math and our calculations, volumes and pressure, you're more than welcome to do so. We're drilling with an oil-based 15 pound per gallon oil-based mud. So I'll say that we balance the well with a base oil, 7 pound per gallon base oil, and we say it took us 30 barrels. Okay? So here, as you can see in this section, the top of the base oil, right, is at 0 feet. And the bottom of the base oil is the top of the drill weight mud, the 15 pound per gallon drill weight mud, which is at 500 feet. Okay? And based on our TBD calculations and these hot drill heights and mud weights, we've got an average mud weight of 14.64 pounds per gallon. Calculated bottom hole pressure of 8,599.24 PSI. So there we have that. We are now at balance. So if we click down here, this little button, simulate at balance fracture, which is something that the software will automatically calculate after a set period of time, or it can be manually set by the engineers on location. It's entirely up to the operator. But for now, we're just going to say that we go ahead and simulate at balance, and we can see that the software has converted itself into pressurized mud cap drilling. So what we see at the top of the screen is depth of fracture. It's all calculated from the previous screen of 12,180 feet, 11,291.46 TBD, and the pressure at the fracture recorded at balance was 8,599.24 PSI. We still have our base oil going down to 500 feet, and below that we've got our 15 pound per gallon drill mud. We have our volumes and our calculated mud weights and our annular surface pressures here, down below. The annular surface pressure, of course, reading 0 because we are currently at balance. We could simply add a few more barrels of base oil to the top to create a little surface pressure against the RCD element. And we see that we have an annular surface pressure of 69.35. Now at this point, I mean, maybe top up with a bit more base oil to increase that annular surface pressure to around 150, but at this point we could start drilling ahead. So we could take it to bottom and start drilling ahead. And let's do that. You'll notice that on the bottom of the mud layers, the drill weight mud, as I start to push the bit on bottom, what will happen is the volume of drill weight mud, the 15 pound per gallon drill weight mud, will decrease. And the reason it does that is because it's being pushed out of the bottom into the fracture. And then here we go, and you can see that the volume is decreasing. Okay? Right, and the reason that our pressures are not decreasing is because the base oil hasn't moved. All we're doing is pushing drill weight mud out of the bottom of the hole into the fracture. Angular surface pressures remain the same, mud weights remain the same, average mud weights remain the same, everything's remained the same simply because all we've done is displaced existing drill weight mud out of the bottom of the hole by putting pipe in the hole. Simple. Okay, so now we're on bottom drilling ahead. So we have our drilling engineer start building a light annular mud at 0.2 pounds per gallon, roughly 0.2 pounds per gallon less than the average mud weight when we balance the well. And that should give us an average of about 150-200 PSI difference in annular surface pressure so that we know the hole's full. So let's just say he's done that. And let's see, we've got our light annular mud. And let's just say we're going to take some of the barrels out. We're just pushing this drill weight mud right out of the bottom, and we'll go ahead and put that tin on top so we've got a full hole. Okay. So now we're drilling ahead, and we started to displace the annulus with the light annular mud. Right now we have a light annular mud from vertical, from 0. And remember, these are in vertical feet. We have a light annular mud from 0 to 166, where the top of the base oil. And then we have the top of the drill weight mud, the 15 pound per gallon drill weight mud at 833 feet. And we're drilling ahead, and we've got an annular surface pressure of 74. Our current average mud weight with these 3 muds in the hole is 14.51, and our volumes and all the things are tracking ahead as we hope. Now, if we were connected to a drilling situation, we would be getting this data from the rig pumps, but we're not. So I'm going to simulate that we're going to start inputting more annular mud into the well by just simply lifting up off bottom and putting it back down on bottom. What you'll see when I lift up off bottom is the light annular mud volume increases. Okay, so as we come out and we need to displace, we're going to be displacing with light annular mud. And when I put the bit back on bottom, the drill weight mud decreases again because we're pushing the mud out of the bottom of the hole. And you'll see as both of those things happen, the base oil top just lowers accordingly, as it would in a real world environment. So we're going to pick the bit up off bottom, and the light annular mud increases as we displace with light annular mud. Again, this would be really just while we're drilling ahead. I'm not connected to a rig right now. So, and we put the bit back on bottom. And as you can see, our average mud weight is changing. Our annular surface pressures are changing, as you would expect when you start to displace the lighter mud on top of a heavier mud, and the heavier mud is leaving the hole. I just want to pause here for a second to point out one of the features of Wellsav. If you remember from before, when we first added the extra 10 barrels of base oil, we had roughly 600 feet vertical height in the hole. But now that we've added the light annular mud, the base soil, the top of the base soil at 1441 is now entered into the tangent section of the well. And so column has shrunk about, not quite in half, to about 391 feet high. And that is the reason for the decrease in annular surface pressure. So where you would have expected to see an increase in annular surface pressure when you add the light annular mud, because this is a deviated wellbore and the base soil is now in a 35 to 40 degree tangent section, it's calculating the vertical height and is now shorter, and therefore it has a less impact on the bottom hole pressure, and therefore we're seeing that as in the resulting annular surface pressure being lower than you would expect. And we'll do that a few more times just to get the hole filled with our light annular mud. And as you can see, once the drill weight mud starts to leave, and you can see as I'm going to stop right here, because what you can notice is that as we continue to displace with light annular mud, the drill weight mud starts to leave, our annular surface pressures are increasing, right? And our average mud weight is decreasing. And obviously the reason why is because we still have the base oil. So the base oil is actually causing us to have higher pressures than we're going to have when we've completely displaced with light angular mud. And that's what we're seeing right here. And as we see the drill weight mud start to leave the bottom of the hole and go into the fracture, we will start to see the pressure, and it's almost there. And here we go, here's the drill weight mud leaving. And now it's gone. Okay, so we have our base oil on bottom and our light annular mud on top. The drill weight mud is completely left, and it's left our screen completely as it's left the hole completely. So it's no longer factored into our calculations because it's no longer factored into the drilling environment. We still have our base oil. We've got 38.9 barrels of base oil. And this is our new average mud weight with the base oil still in the hole, with the annular surface pressure corresponding to this, and all of it measuring back to the TBD at fracture. Okay, and as we continue to move the light annular mud into the hole and displacing the base oil out of the bottom of the hole, then once the base oil is gone, it's gone from the well, it's gone from the hole, it's gone from the software because it's no longer a factor. And now what we go back down and we're drilling ahead at 12,180 feet with a 14.4 pound per gallon mud and an annular surface pressure of 144.19 psi. So now that we're back on bottom, I will again manually, because I'm not connected to a rig, I will manually add some length to the drill string to simulate, let's just say I'm going to make this 15,000 feet long, and that will be able to simulate us drilling below the fracture. Okay, so you see the depth of fracture here at the top of the screen is 12,180, but the actual bit depth here is 15,230. And what you'll notice is that even if I go up and down up with the bit, as long as I stay below the fracture, because the drill pipe is a uniform geometry, it has no impact on the volumes or downhill pressures. So this just shows that the pressures and volumes are all being calculated to the point of fracture, and it's ignoring all of the footage that we've drilled below the fracture. Only when I go up above the fracture will you see the volume start to change. So that's the volume in the hole above the point of the fracture. And one other thing I'd like to point out here is that one of the difficulties, and I'm just going to tack them in while I'm talking, one of the difficulties sometimes is that we'll have what we call the mud rainbow, the rainbow of mud that's in the well, that is sometimes can be very confusing to calculate, especially in holes that are deviated in three-dimensional wells and things like that. So what I'm going to do here, just for fun, is I'm going to throw in a few, and this is not a real-world scenario, but it's still going to be fun for just to show. I'm going to throw in a few different muds on top of the well, And just to show that, and if you guys want to calculate along at home, you're more than welcome to do so. In fact, I encourage it. And again, this is nothing like a real scenario. I'm just kind of doing it for show purposes. If I add, see, as you can see on the right hand side, so far I've got some light angular mud, and I've got some base soil in there, and then I've got some kill mud in there, and then I've got some more drill weight mud in there, and I'll just add one more for fun. I'll take some off of the bottom here, and then I'll add some more light angular mud on top. Because it does happen sometimes that the wrong mud might get pumped in, and you'll catch it, but you still have it in the hole. So this is just to show that even when you have varying different gradients of mud and various different points in the hole, even in a deviated condition, that you will always maintain an exact calculation for your angular surface pressure. You'll always maintain an exact calculation for your average mud weight. Even I could keep tacking muds on and on and on forever. So what we'll do now is we'll just get rid of all those muds by coming up and just going back to just our light angular mud. There we are. The last thing I wanted to show was, when we come out of the hole, we're going to be coming out under pressure, and so we'll be coming out pipe light. So right now I want to just simulate this one thing the Wellsav has in its calculations. I'm just going to say it'll happen at 3,700 feet. Again, I'm entering it manually, but Wellsav has this as an automatic mathematical function in its software. And what would happen, we're talking about a pipe light scenario. At some point, as we're pulling out of the hole, we're going to go pipe light because of the angular surface pressure. And before that happens, the driller has to change over from displacing with light angular mud to displacing with a kill weight mud. So Wellsav has in its mathematics, it calculates at what point we're going to reach pipe light conditions, but it also puts in a safety margin. So it will always inform the driller that pipe light is going to happen well in advance, and that safety margin can be adjusted by the operator to their specifications. So we'll just say, for instance, that the Wellsav has informed the driller that he's going to go build pipe light here pretty soon, and he's informed him at 3,700 feet measured depth. And then so the driller would then transfer over from light angular mud to kill weight mud, and let's just say he puts a barrel on top of that, okay, and he starts to transition to kill weight mud to displace. And then as you can see, as we pull out of the hole from there, kill weight mud is now displacing the well instead of light angular mud, and the angular surface pressures are dropping accordingly. One thing you'll notice here, as the top of the kill weight, or the bottom of the kill weight mud goes into the deviated section of the wellbore, into the build section, the values will still calculate in vertical feet. So the calculated volume for kill weight mud is will take into consideration the fact that now the kill weight mud is entering into the build section of the well. And as the driller comes out of the hole, you can see the surface pressures are decreasing. The kill mud is still displacing the steel coming out. And I should also point out the fact that this condition is in as if the driller was pulling wet. So we're going full displacement, and all of these displacements are in the same way. We're going full displacement for pipe and volume inside the drill pipe. But Wellsav also has the ability for pulling dry, so it will only displace steel. And he's coming out, and we're about to balance the well. And at this point, it would tell the driller that the well is at balance, and to transition back over to displacing light angular mud. And at this point, you could pull the RCD, open the well to atmosphere, and start pulling out your BHA from what looks like 1,188 feet. You can start pulling your BHA, just racking it back. This is a really good feature because sometimes you have a more complex BHA than what we have in the hole right now, and you could use a few stands of BHA, and pulling that RCD is a good thing to do. So this is another feature of Wellsav that really can make the process of coming out of the hole a much safer operation. Well, I hope you enjoyed this presentation of Wellsav pressurized mud cap drilling automation software. As you can see, we've taken various different aspects of the pressurized mud cap drilling process into consideration. We continue to develop the software further, and we hope that you find it as interesting and rewarding as we do. For more information, you can visit us at our website, heraldjavelin.com, and thank you very much for watching.